Hello, and I welcome you all again in this radiation heat transfer lecture series. So, first of all, let me just clear you up that uh, in this lecture series there might be some interruptions, okay, because I am in a bit of turmoil and in a bit of busyness, so that is why I may have to jump into my phone, okay, to see some mails and messages. So, a priori, I offer my apology to all of you. Okay. So, let us proceed. In this video, we will take up some example problem to show you the applications of the formulae that we derived in the past two lectures. Right. So, this is the book, I think you can see. Okay. So, okay, sorry, you can see this is the book by radiative this is the book, the name of the book is Radiative Heat Transfer and authored by FM Modest, okay, or I think it is MF Modest. So this is a very good book. I mean, if anyone is doing his or her research in radiation heat transfer, then this book is a must maybe. Okay, so we will take up this problem. So let me should I do it full screen? Okay, I think you can see it, right? It is saying I will just draw this, okay, don't worry. So question 1. So question 1 says that we have a groove like this, okay, and actually this problem is being solved in FM in the book of Modest, but they have solved it with just with one method, the method of simultaneous equations. But here I will solve in both of the methods, the methods of simultaneous equation as well as the method of I mean electrical network analogy, right? Now here I have taken up mostly the problems of the example, the solved examples, because I want to build a confidence in you that yes, I can do the things by both of the methods and both will give me same answers. Okay, so here some problems are solved in the solved examples. Okay, so that is why you know the answers. Now they have solved in the book, they have solved in only one method and I will solve in both of the methods here, okay. And the problem with this book is I have not found the solution of the unsolved problems. I am not talking about solutions, I am talking about the answer keys of the unsolved problems, okay. So if I had the answer keys of the unsolved ones, then I could have solved the unsolved problems also, okay, but here I don't have that. So I think you can see the picture in the book also, okay. So I have this groove here, okay. So this is the groove, clear. Now obviously this is a solid part, okay. If I hatch this, I think it will be more clear. Now this is 90 degree, okay, this is 90 degree, let me choose another color, this is 90 degree, and it is given that from outside there is an incoming radiation or irradiation, okay. So this irradiation is something like this, it is coming something like this, okay, and it is making an angle of alpha. If I extend this like this, then this angle is alpha, that is even in the question, okay. Now this heat, the value of the heat flux is Q sol, okay, and they have given you a coordinate axis where this is the x coordinate and this is the y coordinate. Clear? Whoops, sorry, I lost the picture. Okay, forget about that. I can remember the question. Okay, so here now the problem says that consider it as a groove and the dimensions are something like this, that I can extend this in this direction, in z direction. Okay, now dimensions in z directions are infinite. Okay, so you can take this as a 2D problem. Okay, or even if you do not take it as a 2D problem, then also it is fine, because in z direction anything will not matter. Okay, if you take any plane along the z, any plane that is parallel to xy plane along z, same thing will happen. Okay, now this side is having a length of a, this length is a, and also this length is a. Clear? Okay, so you are asked that find the total or net heat transfer, not total. So net heat transfer from the groove. Okay, this is the actual question. Okay, so what I can do is, and what I will do is, that is I will just exaggerate these two surfaces. So this is my surface 1 and this is my surface 2. Okay, so what I have taught you in the previous 2 lectures, those theories were applicable for enclosures, right? So here we don't have an enclosure, but can we make an imaginary enclosure? How? Can I join this? Okay, but see, I am joining these 2 points. If I name them by O, A, B, I am joining these A and B points by a dotted line. Why? Because I want to state the fact that this is an imaginary surface. Okay, imaginary surface. Clear? Now what is the, okay, so I should have told you that these 2 surfaces are black. Okay, so these are black surfaces. Okay, so just give me 2 minutes. Okay, so these are black surfaces. Okay, now this is actually environment. This solution, this Q sol is coming from the environment. Okay, and I have told you that epsilon 1 is 1 and epsilon 2 is also 1, because 1 and 2 are black surfaces. Now this is my imaginary surface and this is my surface 3. Clear? Now my question is that what should be the properties of the surface 3? Okay, see, one thing is clear, that if anything, you think very intuitively. Okay, if anything, any radiation energy is going out from the groove. So I am not saying that there is a wall or anything that can reflect this energy back to the groove. So is there any means, according to this problem, is there any means by which the radiation energy that is coming from the groove can be reflected into the groove again. Is there any means like that? No. That means if any energy is coming like this, or in other words, if any radiation energy is hitting this surface 3, this imaginary surface 3, then nothing is getting reflected. That means this imaginary surface 3, I can say, is absorbing everything. And who absorbs everything? The answer is a black body. That means in this imaginary surface case also I should have epsilon 3 equal to 1. Okay. And now I don't want that this surface will emit anything by its own. I don't want that, because in reality, according to the problem statement, there is no physical surface. That means if I take any temperature greater than 0, then I have to consider this extra emission, that is sigma T to the power 4. I have to consider this. But there is no such practical surface having a temperature greater than 0. That means I cannot have the temperature of the surface greater than 0. Okay. That is why I take epsilon 3 equal to 1 and T equal to 0. So you should keep in mind the logic behind taking this. This is very important, because problem to problem you should have that mentality in your mind, that how can I make an imaginary enclosure. That is very important. You cannot take any imaginary additional surface like anything. You should have that much logical sense that this is the practical problem. That is why I am taking epsilon 3 equal to 1 and T3 equal to 0. Okay. Now in the problem there it is also given that the groove is isothermal, that is my T1 and T2 are equal, and I am naming it as T. Okay. So now what I will do is, see, I will solve it by the method of what? By the method of simultaneous equation. Okay. Simultaneous equations. So just let me get those equations for the black body. Okay. So I will just copy this. Okay. So here I have 3 surfaces, so I can have 3 equations. What I need to find is the net radiation heat transfer from the groove. Okay. So you see, practically I don't have any surface 3. That means if I find net, okay, so net radiation, I am writing in short, net radiation heat transfer from groove is equal to net radiation heat transfer from surface 1 plus net radiation heat transfer from surface 2. I think it is clear. I am writing this as Q1 plus Q2. Okay. Now you see, if I define anything like Q3, okay, this is what? Net radiation heat transfer from surface 3. If I define anything like Q3, okay, then because it is a steady state problem, then inside this imaginary enclosure also I must have this thing. Okay, why? Because this is a steady state problem, temperatures cannot change. Okay, temperatures of any surface, temperature of anywhere, it cannot change, and that is why if anything is losing heat inside the enclosure, the other part of the enclosure has to gain that heat. Okay, that is why Q1 plus Q2 plus Q3 must be equal to 0. That means I can see that if I find Q3 only, then also that will be the answer. Okay. So now let us see how can I find Q2, Q1 and Q3. Okay. Now again I can now write this as small q1 into A1 plus small q2 into A2. And what is A1 and A2? A1 is, you can see that if I extrapolate this surface into the z direction, A1 is something like a rectangle or anything like that. So you can see that this you can see that this is A into this length if it is a rectangle. If it is not a rectangle, then it is AL sin theta, right, A cross L. So जो भी हो, I will take it as A into 1, okay, because I am taking it as a 2D thing. So I can further write it as A into Q1 plus Q2, right. So if I find Q1 and Q2, I can find the answer. So in this equation, let me put I equal to 1 and I equal to 2 to find Q1 and Q2, small q1 and small q2. So what I will do is I will again just copy this. So I will copy this and I will paste this here with a smaller font. Okay. So for I equal to 1, let me write this I equal to 1. What will Q1 and what is HO1? We will see that. Okay. Now you see that I have to write. So here this expression in the right hand side, it is varying over j, but the I will be fixed, right. So if I write this EB1, because I equal to 1, right, minus EB2, sorry, EB1 again, okay, then F, okay, so I am not writing A1 A1 I am writing just 1 1 just for the sake of simplicity. Now the second term will be, there will be two terms, sorry, there will be three terms, okay, because this enclosure is having three surfaces. So it will be EB1 minus EB2, right, again F12, clear, plus what else, EB3, sorry, EB1 minus EB3 into F13, right. Okay. So you see here this term is 0, obviously this term is 0, EB1 minus EB1, right. Now this term will be there, and in this term EB3 is 0. Why? Because T3 is equal to 0. Clear? So if I simplify it more, then it will be EB1 F12 plus EB1 F13 minus EB2 F12, right. Then see, I can take this EB1 common, and this is F12 plus F13 and also plus F11, and because 1 is a flat surface, That is why F11 is 0. So adding F11 is as good as adding 0. Okay, so now that means we know that this is 1, the summation of F12, F13 and F11, this is 1. So this is EB1 minus EB2 F12, right? That means my Q1 is equal to EB1 minus EB2 F12, right? Minus what? Minus HO1, right? Okay. So from the symmetry, see here 1 and 2 are exactly symmetric surface. I mean, if I would have given the name 1 to this surface and 2 to this surface, then also the problem description would remain same, right? So that is why I can write for 2, for I equals to 2, I can simply write Q2 is equal to EB2 minus EB1 F21 minus HO2. Now let us see first that what will be the value of HO1 and HO2. See here, this irradiation from outside is coming like this. Okay, now I have already told you that, see, this heat flux is like a vector, not like a vector. There is a vector called heat flux vector. Okay, so you see, if I have to find the net heat transfer through this surface, I have to do heat flux dot n dA and this integral over the surface area, right? And also in radiation also, okay, what we do is, if this is the surface normal n, okay, then what is the radiation flux? I have derived it, not derived it, I have explained it for many times when I was teaching the fundamentals of radiation. So if this is the normal of this surface, okay, then this is what, pi by 2 minus alpha, right? Then my radiation flux will be q sol dot n cap, right? Or in other words, if this q sol I write it as a vector, then q sol is the magnitude, s cap is the direction of this incoming radiation, dot n cap. Now this s cap dot n cap is cos of pi by 2 minus alpha, that is sin alpha. That is why the radiation flux that is going through this surface, it is q sol sin alpha. I hope this is clear. Now this was the actual logic, but intuitively you can think it like this, that this is a vector coming like this. Now this has two components. If I extrapolate it, one component is like this, another component is like this, perpendicular to the first component. So this component is not entering to the surface, it is passing through the tangent of the surface, but this component is directly penetrating the surface. Now if you see, this component is q sol into cos alpha, but this component is q sol into sin alpha. So this argument is like a hand waving argument, but the actual mathematical logic is q sol s cap dot n cap, where this s cap is the direction vector of the incoming irradiation. So here we can see that my HO1 is nothing but what, q sol sin alpha, and similarly this is your homework to prove it, that this is q sol cos alpha. Okay, so we have found out HO1 and HO2. Now see, I have already told you that this T1 equal to T2 equal to T. That means I can write all these things, let me take another color. So I can write all these things, this and this as sigma t to the power 4. All these 4 quantities, right? So the first equation, let me give some name to these equations. Maybe I give this equation as capital A, this equation as capital B. Okay, so capital A becomes, okay, so capital A equation becomes what? So this becomes Q1 is equal to what? Sigma t to the power 4, I will take common, into 1 minus F12 minus Q sol sin alpha. Similarly, now equation 2 becomes, sorry, B equation becomes Q2 sigma t to the power 4 1 minus F21 minus Q sol cos alpha. Okay, fine. So now only thing is remaining, that is to find F12 and F21. Okay, now first of all, without doing any calculation, just because these surfaces are exactly similar, I mean this is a symmetric case. If I consider this surface, that is exactly same as this surface, I mean physically from the point of view of the problem. Okay, I mean the radiation analysis for this surface and this surface, those will be exactly same. No, but there is one difference, that is because this is a bit tilted with respect to both of the surface. So if I consider that I mean from the point of view of this irradiation, these surfaces are not similar, but all the other factors. So what I am trying to say is, the way that this surface sees this surface is exactly same the way this surface sees this surface, and that is why F12 is equal to F21. You can also write A1 F12 is equal to A2 F21. This is the reciprocity rule, and because A1 is equal to A2, then F21 equal to F12. That is also fine, right? So I have to find I mean either of them. So F12 is equal to F21 is equal to what? Okay, now there are two methods. See, I have taught you view factors and the view factors algebra and some methods by which you can find the view factors simply. Okay, I mean just by some formula. So now I mean we will see the application of this formula. Okay, now if you are a gate aspirant, okay, you have an enclosure like this. Okay, so this can be a standard gate question. Okay, so this is 1, this is 2 and this is 3. You need to find F12 or F21. Okay, so it can be a MSQ actually. So they will first give you the option that if F12 is equal to F21, the second option will be F12 is not equal to F21, then the third option will contain the values of F12 and F21. Okay, so how can you find F1 F2 I mean F12 or F21? So the fresh approach by the view factor algebra. So here, okay, I will show you two approaches. The first approach will be the view factor algebra. Okay, so if you are a gate aspirant, then you are supposed to do it by this method. Okay, and there is a standard formula also for any triangle, I think. Okay, and this is actually 90 degree. Okay, so see, we have F11 plus F12 plus F13 equal to 1, F21 plus F22 plus F23 equal to 1 plus F31 plus F32 plus 33 equal to 1. And before anything else, we have this is equal to 0, this is equal to 0, this is equal to 0. So we have how many unknowns? Now we know that this is equal to what? A1 F12 by A2, and this is equal to actually F12 because A1 equal to A2, and this is equal to what? A1 F13 by A2 by A3. Okay, but here A1 is not equal to A3, so there will be a value for A1 by A3, and this is equal to A2 F23 by A3. Okay, similarly now these two values will be equal, A1 by A3 and A2 by A3. That means you have three unknowns, F12, F13 and F23. You have three unknowns, three equations. By this you can solve for F12 or F21. Okay, now the second approach is method of cross strings. Cross strings. Okay, so method of cross strings. So what does it say? It says that, see, what was it? If I have a surface like this and this, okay, so these are the four corners. I will name it as A, B, C, D. So it says that if this is my surface 1 and surface 2, then my F12 is, okay, diagonals, summation of the diagonals. So diagonals means here AC plus BD, okay, minus summation of sines, that is AD plus BC, okay, by 2 into the originating area, that is AB. Okay, so here if I give the same nomenclature to this surface also, then this will be the both the points A and D. That means here AD is 0, and here this will be point B and this will be point C if I have to find F12, right? That means this will be here, okay, so it will be 2 into A. AB is this length, yes, AB is this length, that is this one. So this is A, right? This is 2 into A. Now AC plus BD, AC is this, BD is this, so 2 into A, right? So 2 into A minus AD plus BC. So AD is 0. Now what is BC? BC is BC is this one. So if this is A, then this is A by root 2, that is A cos 45. So this will be 2 into A by root 2. Now that will be root 2A, right? Now A will be cancelled out, so I will be having 1 minus, right, 1 minus 1 by root 2. Okay, so this is the thing I am having. Clear? So if I have not done any calculation mistake, then these are the two methods by which you can do this. So this is your homework to solve it by this one. So this course is actually, you can think about a bridging course between the B.Tech heat transfer, B.Tech radiation heat transfer and the M.Tech level radiation heat transfer. But those who are appearing for GATE also, I have tried to cover it from the very basics. That is, if you are studying radiation for the first time also, you should be able to grasp all the concepts from the fundamental, right? So we got this value of F12, F21, okay. So let us find the final answer. Okay, then the final answer, the Q1 plus Q2 is equal to, we know that it is A1, sorry, A into Q1 plus Q2. So finally this will be A into what? Let us see. A into, so 2 into sigma t to the power 4 into 1 minus f12 minus q sol cos alpha plus sin alpha. Okay, so this is the final answer. Now your homework is to find Q3 if you can. Okay, that is your homework. If you can, you see, you explore the option that from this, I mean, you can write an equation of this type for I equal to 3 also. You write that equation and you see that what are you getting. Now for that I am saying you that what will you take as HO3? What will you take as HO3? So here I am considering this surface as a black surface. Okay, and I am considering that this surface is having an irradiation of q sol s hat dot n3 hat. And I mean, what is the n3 hat? This is this thing. So because q sol is actually leaving the surface, if I have to consider the irradiation, that is why I am considering this minus sign. So this is my HO3. Okay, this is my HO3. Considering this HO3, you find the answer. Okay. Now let me solve the same problem through another method. So I have solved it with the method of simultaneous equations. Now I will solve it by the method of cross strings. Okay. So method of cross string. Sorry, extremely sorry, not cross strings. So I can name it like the method of radiation network. Method of radiation network. Okay, so how can I draw the radiation network for this? Again I will draw the groove first. So this is the groove, let me draw it here. Okay, and finally this. Okay, fine. So if this is my groove, then I will name again surface 1, surface 2 and surface 3. I will write the properties. It is epsilon 1 equal to 1, epsilon 3 is equal to 1, epsilon 2 is equal to 1. This is having a temperature T, this is also having a temperature T, but T3 is equal to 0. T1 is equal to T and T2 equal to T. Fine. And this angle is 90 degree. So these are the black surfaces. For the black surfaces, I told you to start from the surface node. Okay, from the surface node. So I take this as my surface 1, this as 2, this as 3. Okay, so now I will draw the thus the resistances. Okay, so just let me shut off the window because there are some children playing outside, so that will cause some noise, unnecessary noise. Okay, Okay, so let me actually go by very basic. For any surface, let us say that this is my surface 1. You should start with EB1. Okay. Now I will go to J1, and this is R what? Spatial resistance, or again I forgot the name for this resistance. One is the space resistance, another is the surface resistance. Okay. So R surface, and this is what I will just write here, that is 1 minus epsilon 1 by A1 epsilon 1. Clear? Then what? Then see, this surface will have the connection through the view factor thing with the two other surfaces. So let me draw the nodes for the two surfaces. Okay, so here it will be J2 and J3, right? So if I again draw this, okay, so this will be R13, this will be R23, this will be R12. For example, R13 is what? 1 by A1 F13, that is also equal to 1 by A3 F31. Okay, and so this will be EB2 and this will be EB3. Okay, now see, this is actually R surface 1, this is R surface 2, this is R surface 3. Okay, now in the examination hall, if you draw this only, then if I am the examiner, then I will give you full marks. But some examiners, they ask for the actual or the simplified network, and for this you have to draw, what you have to do is, see, this R surface 2, R surface 3 and R surface 1, all the three are 0. That is why EB2 is equal to J2, EB3 is equal to J3, EB1 is equal to J1, right? So what you have to do is, you need to just remove this. I will just copy this. Okay, just this part I will copy and I will paste here. Okay, so you need to draw something like this. So this will be EB1, EB2 and EB3. Okay, now see, if this was the original network, then at any surface the net radiation heat transfer would be indicated by, would be indicated like this. So through surface 1, you know that my Q1 is equal to EB1 minus J1 by my R surface 1. That means whatever will be flowing through this, that will be the net radiation heat transfer. So I say this is my Q1, I say this is my Q2 and this is my Q3. And if there is any irradiation, external irradiation coming from the outside, it is not coming from any surface of the enclosure, then you have to show it like this. So this is the way to show. This is HO2. Okay, this is HO3, this is HO1. So I have shown it by Q1, Q2, Q3. So I must write HO2 into A2, HO3 into A3, HO1 into A1. Right? These are the three irradiations. So if any of the irradiations are 0, then they will be absent. But here, see, you don't have any connection between EB2 and J2 and they are equal. So here you will show the net radiation heat transfers like this. So for the surface 2, it will be Q2, it will be Q3, it will be Q1. Okay, you can also draw an inward arrow that will be indicating that the net radiation heat transfer is inwards to the surface. Okay, that will not alter your answer. Okay, if the actual radiation heat transfer is outward from the surface, then you will get the answer in as a negative number. Okay, and also the irradiations will be something like this. Now irradiation you cannot show by a outward vector, because irradiation by definition is actually falling on the surface. So this is HO1 A1. Clear? Fine. So now let me do it in another way. That is, I need to find the net radiation heat transfer. So I have shown you, if I find Q3, then also I am done. So let us find Q3. So now how can you find Q3? Now see, this is actually a, you can consider it as a, electrical network, as an electrical network. Now you can apply anything that you have learned in your electrical course. Okay, the basic electrical course, or you have also learned in your class 12 when you were preparing for JEE or anything else. So you can apply the Kirchhoff's law, you can apply anything else that is applicable for a electrical network. Okay, so I will just denote this as the current flowing through this as Q23, maybe this as Q13, and see, EB2 and EB1 are same, exactly same. So even if I denote it as Q21, this will be actually 0, because the potential difference is 0. EB2 is equal to EB1 is equal to sigma T to the power 4. So now how can I find Q3? So Q3 I can find by the charge conservation at node 3. So I have used the word charge here, but actually it should be the energy conservation maybe. Okay, so charge conservation is the analogous term with respect to the electrical network. Okay, so what will be that? So at node 3, anything that is entering, summation of the entering is equal to summation of anything that is leaving. So here this is entering, this is entering, this is entering, so those will be equal to Q3. Okay, so we directly got that Q3 is equal to HO3 A3 plus Q23 plus Q13 plus Q13. So firstly let us find Q23 and Q13. So Q13 is the current, and the current is what? Current is the potential difference by the resistance. So Q23 is EB2 minus EB3 by the R23. R23 is 1 by A2 F23. Similarly, Q 1 3 is EB1 minus EB3 by 1 by F1 F1 A1 F13. Fine. So here if we simplify this, then this will become A2 F23. See, EB3 is 0. Then this will be EB2 and this will be A1 F13 EB1. So now see, I can write F23 as 1 minus F22 minus F21, and EB2 is sigma T to the power 4, and for this one I will be having A1 into again 1 minus F12 minus F11 into sigma T to the power 4, right? See again F22 is equal to 0 and so is F11. So this will be A2 into 1 minus F21 into sigma T to the power 4, and this will be A1 into 1 minus F12 into sigma T to the power 4. And we know that F21 is equal to F12. Okay, those things are fine. So finally I can directly write them as, both of them are equal to A into 1 minus F12 into sigma T to the power 4. Both of them are equal to this. Clear? Fine. So I have found out this Q23 and Q13. Now how can I find this HO3? I have already told you that this HO3 is what? Q sol S cap dot N3 cap minus of that, and I have told you the reason of the minus sign. Now we have to find this S dot N3 cap. For this we have to go to the geometry. See, now I will draw it again. Okay. So finding HO3. Okay. So this is my surface 3. Okay, I am drawing an exaggerated view. And this is my irradiation Q sol. So this is the S cap. Okay. And this is the N3 cap. So if this is the angle, maybe beta, I need to find cos beta, because my S dot N3 cap, S cap dot N3 cap, that is nothing but cos beta, right? So I need to find the angle beta. So how can I find that? So see, what do I know is that I have another surface like this, right? And this angle is what? This angle is pi by 4. Okay. So if I draw the same surface but passing through this point, so I have to draw parallel surface. So what I will do is I will copy this one. So copy, paste, and then I will pass through this, right? I will extend it a bit. Okay, now it is fine. So I know that this angle is again my pi by 4. This angle is pi by 4. That means this angle is also equal to pi by 4. Right? Fine. And what else do I know? I know that this angle that this irradiation is making with this surface, this angle is actually alpha. This is given. So beta is equal to, I think you can directly see pi by 2 minus alpha plus pi by 4, right? That means my HO3 is directly, I can write what, minus q sol cos of pi by 4 minus alpha plus what I have written, yes, pi by 2 minus alpha plus pi by 4, that will be sine of alpha plus pi by 4. If I expand it, then it will be minus q sol, okay, minus q sol sin alpha plus cos alpha by root 2. Fine. So that means this term will be what? Minus q sol cos alpha plus sin alpha by root 2 into A3. And we know that A3 is further equal to, this A3 is further equal to root 2 into A. I have shown it earlier. So if now I add all these three terms, now you can do it by yourself, then you will see that I am getting the same expression, this expression. If I add all these three terms, this one, okay, this one and this one, and I know the final expressions of those terms. So if I add all these three terms, you will see that I will get this equation only. Okay, so this was one example, okay, through which I have shown you the applications of both the methods. Okay, so I don't know that how much time have already passed. So okay, I will try to solve one more problem. Okay, so let me go to the book again. Okay, so the book was here, I think. Okay, so I solved which one? Okay, I solved this problem, this one. So I need to, so again let me take another one. Okay, this problem let me take. Okay, consider a two-dimensional enclosure as shown in figure 5.9. 5.9, and what is figure 5? Okay, this is figure 5.9. So we need to consider this one. Okay, we need to consider this figure, this one, and here in this figure you can see that this surface is adiabatic. This surface is having a temperature T2, this surface is having a temperature T3, the dimensions are given, and what it is saying is the vertical surface A1 is adiabatic while the other two surfaces have fixed temperatures. The value of the temperatures are given. All surfaces may be assumed to be grey and diffuse with an emittance of 0.2. So all surfaces, these are very important words, all surfaces are grey, diffuse and emittance of 0.2. Emittance is actually the synonym of emissivity. So epsilon 1 is equal to epsilon 2 is equal to epsilon 3 is equal to 0.2. Okay, determine the temperature T1 of the adiabatic surfaces, of the adiabatic surface. Okay, so now I will not solve this problem with the first method because it is already being solved in the book. So I will explain you. So how can I explain you? So let me open my note also. See, I have derived this equation also. This is for the black. Okay, I have derived this equation here. So this equation and this equation is exactly same. I have shown you that I mean, if you put epsilon I equal to epsilon j equal to 1, then you will get the second equation. So here in this problem, here, in this problem, you are not given any black enclosure. None of the surfaces are black. So that means you need to apply this equation and not the second equation, the equation that we have applied for the earlier problem. So if you apply this equation, then what you have to find? You have to find T1. See, you need to find this T1 here. This T1 you need to find, right? Now, if you need to find T1, I have shown you, I have already told you that T1 is correlated with EB1 sigma. So EB1 is equal to sigma T1 to the power 4. So if you need to find T1, then you, in other words, you need to find EB1. So how can you find EB1? See, you have these equations. So again, you need to see that how many unknowns do I have and how many equations do I have. So your first task for any of these problems, containing enclosures, is to write these equations for all the i's, if you can judge a priori that we don't need to write the equations for all i's, then also it is okay. So for in this problem, they have written this equation for I equal to 1 and for I equal to 2. See, okay. Now you see in this equation for I equal to 1, what is given and what is unknown. See, you have been told that A1 is an adiabatic surface. That means my Q1 is 0. That means my Q1 is equal to 0. All these Q1s are 0. Okay, fine. Do you know Q2? You don't know. And what else do you know? You know this EB2, EB3. EB2, EB3 you know, because you know the temperatures T2, T3. EB2 is equal to sigma T to the power 4. Okay. That means you have two equations, and what are the unknowns? Let me write with black. No, black will not work. Blue. So the unknowns are here this Q2 and what? This Q2 is unknown. This Q2 is unknown. This Q3 is unknown. And this EB1 is an unknown. Then we have three unknowns, but then you will argue that I have only two equations. Then my friend, you have now two options. You can write the third equation for I equal to 3. Okay. But another option also you have, that is again, because this is a steady state problem, you can write this equation, that is C. The third equation, here it is being told, the third equation may be derived by either applying equation 5.32 to surface 3 or by applying global energy balance to the enclosure. So the global energy balance says that because the total temperature, not total temperature is not a correct word, the temperature at any part of the enclosure, or I should say the temperature of the enclosure, is not changing with time. That means the total heat transfer through the enclosure, through the surface of the enclosure, must be 0. So that is why capital Q1 plus capital Q2 plus capital Q3 is equal to 0. That is the third equation. But you can also write the third equation for I equal to 3. See, then you have three unknowns, that is Q2, Q3, EB1, and then you can easily solve for EB1. So this was the first approach, that is the method of simultaneous equation. But now I will solve by the method of what? By the method of radiation network. Okay, so let me solve it. This is question 2. Okay, by the method of radiation network. Okay, first let me draw the diagram. I have one surface like this. This is an adiabatic surface, so I will draw other surfaces through other colors. Okay, so this is adiabatic, so Q1 is equal to 0. T1 I have to find, right? Now this is T2, I think. Let me see in the problem. So this is surface 2 or what? Surface 2 is this. Okay, this is T2. This is given, and Q2 is not given. T3 is given, and Q3 is not given. Epsilon 3 is 0.2, epsilon 2 is 0.2, and epsilon 1 is also 0.1. Okay, fine. So again, this is again a enclosure containing 3 surfaces. Now what is the first step? You can start with any surface. So let me start with surface 2. So for any surface you need to first write the EB thing, EB2. Then you need to establish the correlation between J2, right? The radiosity. This is the R surface 2. Okay. Now R surface 2 is a function of, okay, R surface 2 is equal to, or I should write, this is equal to 1 minus epsilon 2 by A2 epsilon 2. You know A2, you know epsilon 2, that means this is given, right? Now what I need to do is I need to find the correlation with another 2 surfaces. So this will be J3, this will be J1. If there was any other surface, then you should have drawn JK, the correlation, the connection with the kth surface. Okay, maybe there are n number of surfaces, then this would go like Jn. Okay, but we don't have that many surfaces. And also between J3 and J1 we have to build the connections. Okay, fine. And for other 3 surfaces also I need to define this thing, that is EB3. So this one, this is R surface 3, and this is also given because I know A3 and epsilon 3, and this is EB1. Okay, and here it will be R surface 1. This is also given because I know epsilon 1 and A1. So all these things are given. Now I have told you that this is not a complete diagram. I need to draw this as Q2, this as Q3, this as Q1, and also I need to draw this HO3, A3, this is equal to 0, HO1, A1, this is again equal to 0, and we are very lucky to get this also equal to 0. Fine. So you need to find EB1. If you need to find EB1, then you need to work with this part. This is just an intuition. So how can you find EB1? Firstly, we will see that EB1 is having a direct correlation with J1. That is fine. Now if I do the charge balance in J1, how can I do that? So if I write this as my Q21 and this as my Q31, okay, and in any direction this as my Q23. See, you can write a correlation between Q23, Q31 and Q21 by applying the Kirchhoff's law in the electrical network theory. Okay, that you can do. Okay, so I will do the charge conservation. Okay, so the charge conservation at node 1. Okay, if I do that, then see, I mean, what is entering? Q21 and Q31 and HO1 A1, but that is 0, and what is leaving is equal to Q1. So now let us write Q21. Q21 is equal to J2 minus J1 by 1 by A2 F21. Q31 is equal to J3 minus J1 by 1 by A3 F31, and Q1 is equal to, I know Q1 is what? J1 minus EV1 by 1 minus epsilon 1 A1 epsilon 1. Clear? Fine. Then in this equation I have EB1. Now how can I find the other things? Firstly, if I know all the things, so let us see that, what is the unknown in this equation? This is the unknown. Clear? This is the unknown. And what do we know in this equation? We know this term, we know this term, we know this term. We don't know J1, J2, J3. So if we know J1, J2, J3, then we are done, right? So let us see that how can we know J1, J2 and J3. Clear? So first of all, you see that Q1 is equal to 0 because this is adiabatic. So Q1 is equal to 0. Now if Q1 is equal to 0, then I can write my J1 minus EB1 is equal to 0. That means my J1 is equal to EB1. Okay. So here this is equal to 0 because this is equal to 0. That means I have this equation. Ultimately this equation boils down to, okay, J2 minus J1 into A2 F21 plus J3 minus J1 into A3 F31 is equal to 0. Right? So I can take the J1 common and I can finally write J1 is equal to J2 A2 F21 plus J3 A3 F31 by A2 F21 plus A3 F31. It is kind of a weighted average of J2 and J3. Now only unknown is here I mean J1 is obviously unknown, but if I need to find J1, I just need to find these J2 and J3. Now how can I find that? See, I know this EB2 and EB3 because I know T3 and T1. Okay, and I also know R surface 2 and R surface 3, right? So that means, see, I can write Q2 is equal to, so I need to, so see, I cannot do anything like charge, I mean Q2 plus Q1 plus Q3 equal to 0, or okay, if I can do that, so if I can do that, so what I was saying that I cannot do that because that is a logic from heat transfer and not something from the circuit, but still I mean if you can apply that, then this is equal to 0 and then this is equal to 0, I know, because it is an adiabatic surface. Now Q2 is equal to J2 minus EB2 by 1 by epsilon 2 by A2 epsilon 2, and this Q3 is again equal to J3 minus EB3 1 by epsilon 2 epsilon 3 A3 epsilon 3. Okay, so okay, I don't think this will give anything. What I need is, I need J2 and J3 in terms of the known quantities, and the known quantities are T2, T3, epsilon 2, epsilon 3, epsilon 1 and Q1. Okay, so I need another, I need just one more equation for J2 and J3. So this is one equation for J2 and J3, that this plus this equal to 0. I need one more equation. So okay, I will not use this thing. I will solely use just this network. So now I will do the charge conservations at node 2 and node 3. Okay, so let me do the charge conservation at node 2. Okay, see, at node 2 I am having, see, this is leaving, this is leaving, this is entering, but this is 0 and this is also leaving. So everything that is leaving, if I add them, those must be equal to 0. Okay, so Q2 plus Q23 plus Q21 is equal to 0. Okay, so now you see Q2 is equal to J2 minus EB2 by 1 minus epsilon 2 by A2 epsilon 2. Q23 is equal to J2 minus J3 by 1 by A2 epsilon, sorry, A2 into F23. Q21 is equal to J2 minus J1, and J1 is EB1 by 1 by A2 epsilon A2 and F21. Okay, so let's see, sorry, I got a call. me see that who. Sorry for that, I got a call. So here you see that I got the equation in terms of, again, see here I got the equation for J2 and J3. Now this EB2 is known, okay, this is known, this is known, and this is known, but this is unknown, that is fine. Now again, if I write the charge conservation at node 3, then I will have what? Again an equation like that, that will be Q23 is equal to Q31 plus Q3. Okay, Q23 is equal to Q31 plus Q3. Fine. That means if I again write, okay, so let me just write it, it will not take much time. So this will be A2 F23, this will be J3 minus J1 is EB1, this will be A3 31 plus Q3 is what? J3 minus EB3 by 1 minus epsilon 3 A3 epsilon 3. Clear? Again you see I have this equation in terms of J2, J3, these are unknowns, this is known, this is also known, and this is unknown. So from these two equations, from this and this, you can find this J2 and J3 in terms of the known quantities and one unknown quantity, that is EB1, that I need to find. So from these two equations, I can find J2 as a function of EB1, right, and some known quantities, okay, and J3 as a function of EB1 and some known quantities. Now if I put these functions in this equation, then I see, okay, I have, so this J1 is equal to actually EB1. So if I put here a function that is only containing EB1 and some known, and here also a function that is containing only EB1 and some known, then I have converted successfully this equation as an equation which is containing only EB1 as unknown and all the things are known. Then I am done with the solution. Okay, I know that this problem was a bit untidy problem. I mean, untidy means it is a bit longer problem. If you have to solve this, then you need to take some time. Okay, that is fine. So your homework is to match the solution with the example. I mean, the solution they have already done. They have given you the final value, okay, and you need to solve the problem by the method of the radiation network, and you need to match the answers. Okay, so I have solved two problems. Now I need to stop because of the time constraint. In the next lecture, either I will solve some more problems or I will move to the last topic. Okay, that is the radiation heat transfer through the participating media. But don't worry, I will solve some more problems after completing that. And I know that I am uploading the lectures, okay, but the interval between two lectures is increasing. That is because I am also very busy with my personal works, and that is why there is a significant delay between uploading lectures. Okay, so I apologize for that. And so we will meet in the next lecture. Up till that, goodbye, take care, and thank you.